So hello everybody, it's 10 o'clock Finnish time and we are ready to start today's webinar on Edge Intelligence and 6G. So welcome to the webinar series organized by the 6G flagship. This is the 6G Research Reasons webinar series, and this is now the 5th webinar, and we are introducing the 6G white papers that we have published earlier this year. Today's webinar is about Edge Intelligence in 6G. And this is a white paper prepared by an expert group that was led by Ella Peltonen. But as many of you probably know, I'm not Ella Peltonen. My name is Maria Matimikko Blue, and I'm the research coordinator of the 6G flagship, and I was coordinating the preparation of these 12 white papers. But we are lucky to have Ella Peltonen here, and she will be introducing this whole white paper to you very shortly. In addition to Ella, we have two other distinguished speakers today, Dr. Atakan Aral from Vienna University and also Dr. Adrian Kliks from Poznan University. Welcome. And before we start, I would like to mention that earlier this week, we published the second issue of the 6G Waves magazine, which is introducing the research done in the 6G flagship program. And you can find this magazine free of charge in the internet. And there is a dedicated section in the magazine describing the preparation of these all white papers. And there is an article also about the preparation of this Edge Intelligence white paper. So I strongly recommend that you get acquainted with this newly published 6G Waves magazine. So before we begin today's webinar, we recommend that you use your full name in this Zoom profile. And then we have the questions and answers functionality. There's a Q&A window where you can ask questions at any time about the presentations or in general about this Edge Intelligence and 6G topic. There is a half-an-hour session at the end of this webinar, which is fully dedicated to the questions and answers. So at any time, please feel free to write your short questions to the Q&A window. And this webinar will be recorded and the video will be made available publicly in the coming days. You will find it in YouTube. You already can find there 4 webinar recordings of our previous webinars. So it's very interesting to see what these webinars are all about. And the discussions will continue. We will be promoting these discussions in social media using different kind of hashtags that you can see here. So with this, I would like to hand over to Ella. Please, Ella, you are welcome to introduce the 6G white paper on Edge Intelligence.
Thank you, Maria, for the introduction. So, okay, cool. So as mentioned by Maria, my name is Ella Peltonen. I'm a research scientist here at the University of Oulu, hold a PhD in networking and services and computer science. And led by my team, contributing but it's actually a quite big team. So there are all the names who authored the white paper, and in addition we got the comments and feedback from different experts all around the world, both from industry and academia, to provide this vision what the Edge Intelligence would be and what it would mean in the context of the 6G development. Shortly bringing together edge computing and AI algorithms to make more intelligent systems and services for the future of the internet. And in addition to these people, of course, we do have a continuation work where even more people joined, a little bit different names. For example, you will hear today a little bit our ongoing work from 2 of our group members, Atakan and Adrian, about what sort of research there is going on in this area of edge intelligence and what we are looking for to have in the future. Thanks for participating in today's seminar by myself, and have fun with the new white papers, reading through them. So what we aim here in when discussing about edge intelligence, it's all about the real real life systems, real-time systems, real world applications that are not, whether not possible now, or there is some still some resources we need to gather to make things happen. Today we are discussing about the vehicular computing a little bit more further, but that vehicular computing is only one, or autonomous vehicles are only one area. Here we can see different application areas in healthcare systems, remote healthcare, digital surgeries, manufacturing, smart traffic, smart cities, and so on. So it's all about the real world applications, and it's all about the real-time systems, real-time data management, real-time dynamic networking, and bringing the intelligence on the network. Oh, sorry. So what we currently have, the Internet of Things is the main enable, or the main kind of topic we are discussing usually when we consider something where we collect the data from the sensors, we run some machine learning algorithms, we provide results, and we make an effect on environment or the system based on what we have learned from the context of the device, or context of the user, context of the system. And that's an old thing, of course. We do have Internet of Things. We do have machine learning for different applications already. And whenever we go further in 5G, we get more latencies and capabilities to run even more complicated machine learning and artificial intelligence algorithms on top of the cloud systems. But these there are some issues we have defined in a white paper which are not yet solved in intelligent networking only. We need more dynamic solutions to make things happen really in the real time without the cloud, or with the support of the cloud, but also partially doing some learning, some data management tasks in the local devices. Important here, when we're discussing the edge, we choose to use the word edge as a kind of like umbrella word, where all sort of computational capacity, networking capacity devices, which are not part of the usual cloud infrastructure, they can be local servers, they can be local devices, or they can be the traditional edge services in the network core. So we are not limiting on what we mean, whether it's a fog, mist, or just edge. We're just kind of giving the umbrella of the edge, all capabilities. We have to have this future system where everything is super dynamic, super adjustable, and learning by themselves. To achieve this sort of a big future where everything is intelligent, everything is connected, we need to have a practice and different fields. We need to consider different computer science topics, but also end user aspects, social sciences a little bit, things like that, business issues, how to monitorize these things, yes, of course. But in the core computer science, we are interested in the networking itself, AI capable devices themselves, low energy devices, but not only those. So we are interested in everything, every devices in the network who can run computational capabilities and can run AI intensive tasks, whether they are small or bigger, but because the power is coming from the network of all of those devices. Of course, we need a theoretical work from a machine learning perspective to get this. We need networking work. We need distributed computing people bringing capabilities. We need security and privacy aspects, but also providing opportunities for running the AI systems itself. It will make the network itself more intelligent. So it's not only about getting fancy AI applications running on the edge, but also making the edge more intelligent by having those AI capabilities available. So it's all about making the decisions automatically and dynamically what to compute or / communicate, where that should happen, when it should happen in the real-time system, and how it should happen. So all these decisions to become dynamic to provide these more autonomous decision making on the edge whether the application is the network core itself or some fancy AI autonomous core. How to go there? So we are here somewhere in the beginning of this roadmap. and currently we do have edge computing, mobile edge computing deployments in the 5G. We do have AI and machine learning models pre-trained on the edge we can utilize. And what we are looking for currently, the development of, for example, federated learning, is to utilize those capabilities even more intelligently. But we need truly distributed AI to be run there without the centralized systems. And of course, whenever we are discussing about the future of internet, we will necessarily need to consider what sort of hardware we have in the future, what sort of security and privacy aspects we have in the future, what sort of learning capabilities we can have in the future. And all of those aspects will lead us in 10 years or 20 years towards this vision we have provided in the white paper. If you're interested in, please have a look at the current white paper. And we are currently providing a continuation. It will not be a white paper, but continuation paper for this to give more detailed views to what the edge intelligence should be. Okay, keeping it short, just to highlight a couple of issues and topics we discussed and why this is so important expertise area is to bring together different backgrounds of people. So we do have a software people in the expert groups. We're thinking these issues. We have a theoretical people, we have networking people, and we have user people. We need all of those capabilities to really figure out what does it mean to have like this sort of edge intelligence. Okay, cool. If you're interested in, especially if you are Finland, we do have a special interest group. Even outside Finland, you're welcome to join the activities. We do organize workshops, seminars, currently, of course, mainly webinars. New articles are coming. If you're interested in, go to this website. The stuff is organized by together with two flagships, 6G and the artificial intelligence flagship, just to broaden up the theoretical side. And please feel free to contact me if you have any questions or you're interested in joining the activities in the future. Thank you, and I think we can go to more technical program of the day.
Thank you, Ella. So I strongly recommend everybody to have a good look at the white paper on edge intelligence. And if you're interested, just contact Ella for more further information and future activities. So the next presentation will be given by Dr. Atakan Aral from Technical University of Vienna. The stage is yours.
Thank you. My name is Atakan Aral from Vienna University of Technology. So today I will talk about distributed training under node and link failures. Our research is funded by FWF, which is Austrian Science Funds, for the project Raccoon. Our PI is Professor Ivona Brandic. And I will talk about most recent finding of us in this presentation. So I would like to directly start with the motivating example. And for this, I would like to use smart grids and electric vehicles. So smart grid is all about the automation of energy generation, transmission, and also consumption. So there can be several opportunities for optimization here, software-based optimization, such as capacity planning, transmission controls, and charge planning. And with this, all these technologies require a significant amount of intelligence. And with intelligent decisions like avoiding peak load or reducing the loss of energy, it has been shown that only with charge planning for electric cars, it is possible to save 110 gigawatts of energy per year, and this amounts to 37,000 of today's average wind turbines. So, as I said, intelligence plays a role here, and maybe the most difficult part of it in charge planning is the intelligence at the vehicles, electric vehicles themselves, mostly because they are mobile. So here we envision an architecture supported by supported by roadside units that are also equipped with edge computing servers that can collect the data from moving electric vehicles and train local prediction models themselves. So in this scenario, there are several issues to be addressed. First one that we call insularity. This problem is caused by the limited range of roadside units. So these roadside units can collect data in a specific geographical area only. So the model that they are training are insular or limited to what they see in a small geographical area, which may not generalize very well or may not be accurate at all. So the first issue, as I said, is that insularity. The second is non-stationarity. The environment in this scenario is highly unpredictable. So there are frequent changes so that this local prediction models have to continuously update themselves. And the third problem is, like any distributed system, is a big problem that the connectivity cannot be trusted. So there can be, for example, in this example, the vehicle can be out of range. It can be in a tunnel, or simply one of the roadside units or edge nodes might fail. And this results in loss of certain data. So our solution in this architecture to solve this problem is to use a centralized parameter server, which synchronizes these local models and redistributes them to the distributed edge servers. So back to some definitions. So edge intelligence is defined as the effort to make the most of the widespread edge resources to gain AI insights. And so Professor Satya, in one of his pioneer papers for edge computing, already defined the benefits of using this kind of distributed or local proximate resources. And these are first, the services can be highly responsive. They can react to the changes very quickly. And the second one is scalability is improved. The third one is when cloud fails, there are outages, the local processing can continue without losing the service. And finally, since the data is not accumulated in a centralized server, privacy is better enforced. So we argue that these benefits of edge computing also applies to edge intelligence. And today I will specifically talk about the items 1 and 3. So responsiveness of how to achieve responsiveness with edge computing and how to achieve reliability. So as I said, there are these three problems of non-stationarity, insularity, and intermittent connectivity. And we identify two types of solution directions for these problems. The first one is the reactive solution, that what to do after a failure happens, after some data is lost. So how can we recover from there? I will talk about our most recent work, stainless control, on these reactive solutions, you can find some links to our recent papers here. And the second solution is the proactive one. So what can we do even before failures happen? How can we have a more failure resilient edge computing system or an edge intelligence system? So let's start with the reactive one first. So here I will give an example, and it's a trivial example with only 4 vehicles. And here we are seeing from the perspective of that centralized parameter server. So as I said before, the purpose of this server is to synchronize local machine learning models in a more general model and redistribute it to the edge nodes. So from the perspective of this parameter server, we have a timeline where we see the arrival times of the updates from each electric vehicle. And at the bottom, you see the overall accuracy of the prediction averaged and over time. So in the beginning, we already have a prediction model at the edge nodes, but its accuracy deteriorates over time. The reason for this is staleness. So the model is not fresh anymore, but the environment changes quickly. So we have to update this local model somewhere. So otherwise it will, as I said, the accuracy will deteriorate. So let's say at a specific time t0, we have information from only 2 vehicles, vehicle 0 and vehicle 1 at the parameter server, and the other 2 are missing for some reason. For example, there's a network failure or node failure, any kind of failure actually. So the first solution could be simply at time t0, we can build our model, our general model, and redistribute it to the edge nodes. This way, we will refresh the model, so it will be again more accurate. It is not still using the whole information to generalize, but there is some information, and we will avoid this low accuracy for now. So the second solution could be wait for a little longer, get more information. For example, in this example, we also have data coming from vehicle 3. So at time t1, we have more information. We can build a more general model, maybe more accurate than this green one. But the cost is we have to tolerate lower accuracy of the stale model between time t0 and t1. And of course, there is also the third extreme solution to wait for all updates to arrive at a later time t2, so that we will have the most general model, but we will have its latest. So the question we were interested in this work is to how to dynamically choose between these different solutions. And I say dynamically because there are the decision is very unpredictable, because we don't know when we will get updates from which vehicle, how significant the update will be, because here I show that the accuracy always increases with more data. This might not be the case, because new data might not be that interesting, so the accuracy stays the same and you wait in vain. So as I said, there are very unpredictable income inputs to this problem. So the solution that we found was to use also reinforcement learning to optimize this problem, to find the best solution at each iteration. So one question could be, why not simply build the model at t0, then at t1 and t2? This is something we want to avoid because of in this example we have only 4, but normally we would have thousands of vehicles to optimize, so we don't want to overload the network with updates. That's why we choose a single point of update at each iteration. So our results show that we can achieve comparable accuracy to core AI, which means collecting all the data at, for example, cloud data center and processing there. So this is the optimum case for accuracy, but not for latency. So we managed to have comparable accuracy to that, and yet we have real-time responsiveness. So we use the age of information metric, which showed us when a new data point is collected, how long does it take to that data to be incorporated to the models. And we show that in our algorithms, we could do it in less than 10 seconds. And we also show that the communication overhead is very low, so it can run in real time. And we only have to do one synchronization per minute, or less than one, even in some cases. So yeah, this work was the first famous control mechanism where this synchronization period is not fixed. In the literature, usually static periods are used, so we show that dynamicity helps here. So the next solution that I previously talked about is the proactive one. So this one is about before failure happens. So what can we learn from historical failure traces so we are better prepared for future failures? So again, we have a trivial example here with only 3 edge servers. And there are some dependencies between the failures in these servers. And of course, we show this with real data that actually there are spatial and temporal dependencies between edge computing failures. So in this case, in this example, one of the reasons is that server 2 and server 1 share the same power grid, and server 1 and server 3 share the same communication infrastructure or the same network. So if this network fails, both S1 and S3 will be unavailable. So their failure is correlated because of this shared resource. Of course, in real systems, we don't know about these dependencies. We don't know why they are dependent, but from historical data, we can find out that they are dependent without knowing the root cause. So another reason of dependency here is workload offloading. So these servers are configured to offload their work when they are overloaded. So when S1 is overloaded, it offloads to S3, and when S2 is overloaded, it offloads to S1 and S3. So this is another reason for dependency in failures. Particularly, this one is called cascading failures. So if a failure happens in one of the servers, it could be cascading to the others. So we show that we could model these dependencies as a graphical model. So a failure in a certain server at time t is dependent to other failures at different servers. And we can even have dependencies in different time steps. So a failure at server 1 at time t minus 1 could cause a failure at server 3 at time t. So, and we also showed that we could extract these graphs solely using the historical failure traces in a fairly accurate way. And of course, these graphs are also complemented with so-called conditional probability tables, which shows for each node, for example, this one is for F1T here. So it has 2 incoming edges. So based on the values of these incoming edges, so the failures in previous time step or the current time step, there is a probability that this node will fail or not. So using this information, we could select which edge nodes to utilize for any service. It could be this smart grid service, or it could be any intelligent service running on the edge. So we can deploy it in a way that the failure probability is minimized. So we show that we can achieve availability that is comparable to the cloud, which is in usual case 4 nights of availability. And we could do this using very unreliable resources. We assume that the edge resources would be significantly less reliable, depending on the definition of edge, of course. But in the data sets that we used, the availability range from 44% to 91% of availability. So with redundancy, of course, we were able to achieve a high level of availability. And compared to the state-of-the-art forecaster for failures, we managed to achieve both higher availability and lower redundancy. And to the best of our knowledge, this was the first application of a probabilistic model to edge reliability. So coming to near the end of my presentation, I would like to point out for some key findings for distributed training. First of all, I would like to mention the 8 fallacies of distributed computing by Peter Deutsch. And the very first fallacy is to assume that the network is reliable, which is of course can be wrong in many cases and can have catastrophic outcomes if we make this assumption. And we also show that failures can reduce AI performance significantly if we don't handle them properly. But the good news is, if we use some intelligent communication techniques or some redundant deployments, we can eliminate most pitfalls in these unreliable systems, and we can achieve high performance edge intelligence in that case. Of course, there are several open issues. For example, how can we make this decision in a fully automatic way? And how can we continuously improve and continuously learn from previous mistakes or successes to improve our decision engine? And another problem is, how can we generalize these algorithms to any artificial intelligence or edge intelligence application? Because currently different algorithms need different techniques to solve the problems. And also an interesting direction is also to reduce the overheads, because these systems need to run in real time. So that is the end of my presentation, and yeah, I'm looking for questions at the end. Thank you for listening.
Thank you very much for very interesting presentations. And you have the opportunity now to ask questions. So type your questions in the Q&A in the Zoom window. And then at the end of the webinar, we will have at least half an hour to go through those questions and answers. So thank you, Atakan. And next we will move to Adrian. Adrian, please.
Okay. So welcome you. Good morning, good afternoon, good evening, depending on the place in the world where you are now. So it's my pleasure to present some observations, some comments on the topic. What you can see now, I will, in some sense, I will continue what Atakan said previously, but in that sense that I will focus on autonomous driving and platooning. Here I will touch a bit different aspects of this scheme. So based on some measurements and some experiments we have done with real cars, and also some predictive maps. We will try to show how this edge intelligence could be applied in such a scheme. So my name is Adrian Kliks, just to say once more, and this part was also prepared by my colleague Paweł Sroka, and we represent Poznań University of Technology and our recently established spin-off company Remedial Labs. So the topic of this part is at the end, as I said, is edge intelligence-based autonomous driving and platooning, and we will now try to deal with some requirements, challenges, and applications to show simply why and how it could be helpful. So it will be some other viewpoint to the previous very nicely talk by Atakan. So let's continue. So if you look what is happening, so it's nothing new, but just look briefly on some sort of history. Without any product logging, it's just some selected cars which have been said to be autonomous. So if we start in 2014, on in fact even earlier, there is a nice march toward fully autonomous cars. So different companies produce different cars. All of them are more or less autonomous with this or that level of this performance of this autonomicity. And different kind of cars. So these are more for private use, and on the right side you have more for public use. So if we look at this, at these cars, these are of course autonomous in that sense that they are using intelligence somehow applied within the car. So these are really driving autonomously. It's a good way. It's a good word, in fact. But also there's another option to improve it, to improve the security and reliability of such a network, as it was mentioned previously by Atakan, to add some also intelligence in the, on the edge. So to improve the, as I mentioned, how the entire network simply functions. So it's important also to think about that and see if there are some ways how we can improve it. If you look more details, what are the options? Also, these options are mentioned directly within the 3GPP documents and simply within the ongoing documents for the new 5G standards, for the new releases. So in release 16 and also in 17, there are these three. So these are highly considered that will be applied in practice very soon. So we have these three, I mean, there are more schemes, but we can mention these 3 or 4 schemes. So the first scheme, which is on top, which is called extended sensors, simply in that case, what is happening is that we have different autonomous cars. They are performing some sensing and they can communicate between each other, but in fact, they are somehow autonomous, but they can perform mutually some measurements and to exchange this data to improve the reliability of the driving. But more important probably is the I mean the next step will be simply the middle case where we have autonomous or remote driving. Autonomous, which is as I showed the previous figures, previous photos of existing cars, where the car is driving fully without the help of the human driver, but with the support of the infrastructure. Or we could have remote driving where we have either the human or intelligence located somewhere else that drives the cars remotely. So this is most challenging probably a case, of course, if we concentrate that every car is driving in that way. And probably, it's my private opinion, one of the probably closest to realization, maybe not, but I suppose that is this platooning case, where simply in addition to this cooperative, I mean CACC cooperative control of cars, where we can measure the distance and automatically, I mean, slow down the vehicles and so on. We can create a platoon. So Platoon simply is we can say is a set of cars driving one by one. It's simply, let's say, a train of cars where there is one platoon leader, or maybe more, but in general, there's one platoon leader who controls the driving of the cars beside it. So behind it. So simply, we can say that we have a train of cars. The issue is that when we reduce the distance between these cars, simply we can significantly reduce the fuel consumption. So all the logistic companies, the spedic companies, they are highly interested in this application. So also they can eliminate the need for human drivers. So simply, this is the case with. This is my private opinion that it could be one of the first ongoing and really applied solutions in real life. But we have this three cases: so extended sensors, autonomous and remote driving, and this platooning. So all of them have different requirements and different challenges can be identified for these specific scenarios. These are listed here. These are based on exactly from the 3GPP documents. I mean, 3GPP, I mentioned this because as all of us know, there are a lot of companies involved here, and within this particular group, I mean, all these requirements came from all these companies. So these are well-established data. So some of them may be surprising, but in general, if you look on, I mean, there are four scenarios. This platooning, advanced driving, this is autonomous driving, a different name of it, extended sensors, and remote drivings. There are 5 columns, I mean 4 columns which specify the requirements. These requirements are to be addressed within 5G and its extensions, also to be improved in 6G, right, in 8-10 years from now. So regarding the data rates, up to 65 megabits per second platooning, advanced driving, they estimate that it should be around 50, and extended sensor, if we have a mass deployment of cars and a lot of data to be transferred, and we have this even 1 gigabit per second. Then regarding the latency, this is the maximum latency we can allow. For the communication part, so we have to remember that what is very often missing in the discussion is that if we apply some sort of edge intelligence, some computation somewhere, and some reasoning outside, then simply it takes time, as it was also discussed previously. And this time will also have impact on this overall total latency. So the required latency maximum, let's say, if we look on the lower boundaries, it's 10 or 3 milliseconds. So if this is the requirement, 3 milliseconds, so then this information exchange and reasoning within the edge intelligence architecture or elements has to be also very extremely fast, I would say. So then, if you look on the reliability, 4 or 5 nines, which is the top, the upper boundary, and depending on the because you want to raise the question why we have this 90% here. 90% is because we may have platooning, but we're still there is a human driver inside. So this intelligence is to support the platoon, but also support the human which are driving these cars. And the range in terms of communication, which is the range required to send messages. Okay, so these are the requirements. And if we look on the challenges which can be associated with these scenarios, these are listed here. I have identified with my colleague, we have identified 6 of them. These are also in line with previously all the previous speakers mentioned. So there is a strong need to make a mobility decision much faster than the human driver. So we have to reduce the latency below this milliseconds. As it was mentioned, significant amount of data, which is the second one, and also the need of a fusion of large volume of data, different type of data, and also appropriate reasoning. This is very important, very I would say extreme challenge how to do this with these requirements on low latency and the high reliability. And as Atakan mentioned, we have this high dynamics of the network, so everything is simply changing. So the scenario is not that easy, not stable, and we have to perform decisions very quickly. And usually there is, if we look at the what is happening now in the distributed cases in ad hoc vehicular networks, usually there's no central controller. If there could be any controller, it should be placed probably or not probably somewhere on the edge. So these are the challenges. If we look, because our experiments, which I will show and describe briefly now, this relates on the improvement of reliability of wireless communication parts. So how we can apply, so the question was how we can apply edge intelligence, all the algorithms placed there to improve the communication, so increase the reliability. So just to briefly recap to all of you what is happening in the wireless communication for autonomous driving. So if we have V2X, so V2 everything communication, we can split it in two parts. On the left side, we can have everything which is fully distributed. This fall under the umbrella of DSRC, so dedicated short-range communications. And here we have solutions based on IEEE 802.11p. And if you look on the medium access part, this is the wave part, wireless access in the vehicle environment. So in a nutshell, on the left side, all the decisions are made in a distributed way. On the right side, in terms of communication, we are using the infrastructure provided by the cellular operator. And simply, that's why we are talking about C-V2X or cellular V2X. So there are two different options, either to use licensed band or unlicensed band. Centralized decision with the support of existing infrastructure, and distributed where we can rely only on ourselves or on the roadside units, and all the problems with insularity and all the stuff may appear immediately. So what are the problems? If we look, as we know from our everyday life, if we look on the Wi-Fi applications, so we are observing the problem of congestion. So the same is happening based on different experiments and simulations. The same is happening or may happen in the 5.9 gigahertz in control channel, which is required for reliable V2X communication. And simply what we're considering is if we can move it somewhere else, whatever. I mean, it was not important that it was TV white spaces, but it could be anything else, any other band of interest. We have selected TV white spaces because of the stability of DTT transceiver to see if this concept works. But the idea itself is to move the traffic from this congested channel to somewhere else. This scheme is widely known as vehicular dynamic spectrum access. And in order to make it work and make it reliable, we need support from the infrastructure. As I said, the location of the digital terrestrial television transmitters, these are rather stable. Usually also the allocation assignment of TV channels is also stable. So it allows us that we can offload some traffic, as I said, from this congested CCH to some other bands like this TV white space. And the use of edge intelligence to perform VDSA seems to be necessary, and we will show if it can work. So all the tools, they need to collect data from many vehicles, and simply in our experiments, the goal was to support the vehicles to select the best channel, either to stay in Wi-Fi or to move to TV white spaces, and if yes, to which band, and if there are many platoons in the vicinity, how to automatically in real time change the communication channel. So the architecture which was considered, okay, it was not built directly on the road. We made just some measurements and then to post-process it in that environment. But so we have assumed that, okay, there are different platoons. So one platoon, the second, and then the other, they are communicating between themselves. Using some even high frequency channel. And also there is a platoon leader that can communicate with some, for example, roadside units or simply with the cellular network. Then we will have some regional domains, databases and processing units, at least how we have envisaged it in our experiments. And these are deployed here to perform real-time decisions associated with some certain location. Of course, we will have a global domain controller, global domain database, and processing unit for inherent for reasoning and async reasoning and some suggestions which will be provided to the local reasoners, which will then distribute, make decision and distribute the decision to the platoon. This is the scenario and the architecture we have considered in our case. And simply we perform some measurement. This is just a glimpse of the measurement results and how we have built the model within the database. So this is the fragment of road. We have measured the received, because I forgot to mention, of course, we can move to any other band only if we do not cause harmful interference to other existing services. Yeah, so this is, ultimate requirement not to disturb the others. So first we have to locate we have to identify the locations where we can simply start the transmission. So what we have done, we made some measurements on different TV channels. On this figure, we just show two of them. The green one is for 490 megahertz and the black one is for 552. And we have observed some changing values of the received power from the DVB-T. So if everything below this violet line, we can set that there is no signal. Everything above that line has to be protected. So what we have done in this local databases, we have stored the approximation of the changes as a function of distance. So this dashed line is the approximation of this very sharp curve, and these were stored in the databases to improve the decisions made by the platoon leaders. The scenario which was considered was the following. So we have different houses, different premises located along the highway. There were two platoons moving on the outer lanes of the street. Many other cars. There is a dedicated jammer, so the cars to increase the traffic in the 5.9 gigahertz band. We apply this cooperative adaptive cruise control. And also we try to move all these cooperative awareness messages from 5.9 to other band. And the results, simply remember that we have to achieve, depending on the scenario, we have to achieve either 99 of the reliability or at least 90. Yeah, so we are dealing with the autonomous driving. So simply, let me just summarize what we have done. So we have measured where there are DVB-T signals, and then simply we perform some predictions when there is a car driving here and there is a car from the opposite direction and also driving there. The database was performing some decision suggestion. Okay, this platoon leader, please move to channel number, let's say 2, and the other one, please move to channel number 3. And when they passed, then simply they can switch to different channel in order to first keep the throughput as required and also increase the reliability. Also, the other gain is that we reduce the congestion in the 5.9 gigahertz band. So what we can see that if we apply just this, I will describe it briefly. If we look at this blue bars, these simply show that if the channel is congested, of course, the probability of successful reception is going down. So the cars within platoon will observe some problems simply. But if we apply this very simple model where this intelligence applied and some prediction is applied based on measurements, we can, I would say, significantly increase it. Of course, we may say that there are small change in numbers, but still remember that we are saying about the reliability and we are dealing with some 99.9, and this is the goal. So simply by applying such algorithms which are deployed somewhere on the edge, we can improve it. So this simply proves the concept and that it will work also in such challenging scenario. So what are the conclusions from this real-time experience and not experience, experiment, sorry. So is that it is possible to reach the required communication reliability, or at least to improve it with the support of edge intelligence. Of course, this is a generic conclusion, but due to the high dynamics of vehicular environment, everything should be self-organizing, so the support of the infrastructure may be beneficial. So AI should be able to process large amount of data, deal also with this age of data when it will be used or useless. We have to minimize data processing latency. This is highly this really demands in the autonomous driving case, where we have this latency of 3 milliseconds. So if there is something for communication, we have to also take something for this processing. So it has to be extremely fast. So all the models, all the trained models and data within the infrastructure has to be also very, very fast. This should be scalable, and sharing of fraction of data between different elements of the infrastructure is also a vital option. Okay, so I hope that you get the main message from this talk. So regardless of the scenario that we try to see if VDSA is working or not, the main outcome of this is that simply by applying some predictive tools located, and let's say we can say there's a mixture of fog probably and edge, but mainly on the edge we can improve the performance of the system. So it's a good message, and also it paves the way for further research and edge intelligence. So thank you also, and we can probably start the question parts. So Maria, I give you the screen back.
Thank you, Adrian, very much for your presentation. And all these presentations will be available in the event website after the webinar, together with the recording. So now it's time to move to the questions and answers section, and you still can write your questions in the Q&A part of the Zoom webinar. We already have received several questions, so let's go through them. The very first question is, how synergic is the current situation between works of edge computing and edge devices? Is the collaboration strong enough to support a good pace of the computing development? Are the device, or should the device aspects be more engaged in the process? Who would like to answer this?
I can give a short comment on this. So I think by edge device here is meant user devices at the end of the network. So there are several works, at least on the research field, that consider edge computing solely formed by these kind of low capacity and better limited devices. And there are even technologies to run deep neural networks on end devices only, which is, I think, the extreme case. But yeah, I think there are initial efforts in this area.
Thank you. Then if we move on to the next questions, there is a question about how can we choose proper machine learning models according to the different vertical scenarios? Ella, would you like to answer this question?
Yeah, this is really one of the research questions we are looking for. So this is a very core of the whole development, because choosing models dynamically depending on the context of the situation, or bringing the context-aware processing of the models is an ongoing research question. And to understand, first of all, inside of one vertical, we need to consider which sort of capabilities we have in the situation, what models we have pre-learned, what we can do online, current situation, considering the available computational time, latency, and available computational resources and pre-trained models. And so the first question is, of course, look at inside of one vertical, what the situation requires. And then when switching between the verticals, the generalization of those models will be another question again, because then we need to talk about how generalized is the data, what we can actually transform from one vertical to another. Of course, if we have like multiple verticals that utilize the same sort of models, like we have several verticals needing for weather data models. For example, we do have autonomous cars, and on the other hand, we have what would I say, like a system that requires weather information for air quality tracking in the urban environment or something, so then those models, of course, will be shared between the verticals. But we need to always consider what's the data, what we need from the data, and what's available and what we can learn. So it's part of the research process, really, how to generalize the models, and is it possible in general. Thanks.
Thank you, Ella. There's one question about what is the suitability and applicability of 6G as enabling first aid in remote areas and in surroundings where city center healthcare services are not available. And we actually have one white paper which is dedicated to these remote area connectivity challenges and solutions for that. So that is an important topic. It will have to be taken into account in the 6G development. And actually one of our expert groups has worked on that, and you can check out that white paper.
Yeah, and I have to add these, the healthcare mentioned, the healthcare vertical here, for example, bringing remote sensing for people far away from healthcare services. For example, they do have a virus infection or something different that need to be monitored in their home environment, but the data processing can be done locally to in that location where your patient is, and just a certain information delivered to the hospital or care providers in real time, so that we can support the patient even if they don't have access to the healthcare services immediately. This is just one use case, and different sort of healthcare services ease them to provide them, for example, for the countries where there is, for example, not a specialized surgeon on some very rare brain condition or something. Maybe we can have this external expert participating in the surgery in real time, because we do have a very, very good real-time latency and a local data processing, so that we can bring that person to help in the surgery in a remote condition. So such an effects are all part of the 6G development, and I think this also links to the sustainability in remote areas and third world countries and developing countries. So it's also part of the Maria's own white paper. Actually, it's a very good question.
I would just add, if I may, Maria, simply because I was also involved in this remote part. So as an extension to what Ella said, is that simply if you look at SAGE as in general a technology that enables a coverage to, everywhere. So simply it is really then, it should be, or what we expect is that it should be really an enabler to healthcare, but also to any other application like that. So as we have these requirements, one of the stringent goals is to guarantee this coverage really everywhere. If we say everywhere, it means really everywhere. So that's the point.
Thank you. Then there's one question dedicated to Atakan about his presentations, there are more clarification questions. So you mentioned that failures can reduce AI performance and that intelligent communication can eliminate most pitfalls due to failures. Can you elaborate a bit more on the intelligent communication approaches that can be leveraged, and which of these do you think are the most promising to address the pitfalls?
Yes.
Two of the pitfalls of Deutsch are the topology does not change and there is one administration. So how could these challenges be addressed?
So it's a very good question. So thank you for asking for this. Actually, there was one more question at the bottom that says, how can we have intelligent collaborative for edge communication, which is also similar. So I will try to answer both together. First of all, we need to think why we need communication for edge intelligence, because the main idea is to process data locally. So on paper, we don't need to communicate the data to anyone, right? But one of the reasons where communication is needed is like the example that I gave is where the models are only fed with local data, so they don't have a global view of the whole problem. If they are deployed in large scale, each one is focused on its geographical area. So one of the reasons for communication here is to synchronize these models to come up with a more general one, so that we have better prediction performance, for example. So coming to intelligent communication approaches, what we have tried was to use reinforcement learning, because it helps us with highly stochastic environment and helps us to address unpredictability. So specifically, we used Q-learning. There are variations. Deep Q-learning could also be applied here. But of course, this is a very new problem, and we are in the beginning of it. So there are also various future application areas or research directions that could go in this way. What we also tried was to use multi-objective optimization to come up with, for example, to address the trade-off between energy efficiency and edge intelligence performance. This was another approach that we took. So this is for the first question. And for the second question, so two other fallacies of distributed systems are mentioned. So topology does not change is also a fallacy. Topology might actually change. Yes, and for now we haven't addressed this in our research. So we try to be agnostic to the topology. We assume that if nothing fails, the data somehow reaches the parameter server, and we try to be not interested in which route it took on the way, but yes, definitely this is something that can also cause problems in synchronization, particularly. And there is one administrator. Yeah, this is also a policy that to use a single point of failure, actually, like a parameter server. So we are also interested in going more decentralized in this field.
Thank you.
Thank
Then
you.
there is a question about decision making, and a comment that it seems that large part of the problems boil down to decision making, decision theory, reliability of the decisions. So do you think that the decision toolboxes that we have available would be at the ready level of this autonomous decision making that is needed? So what do you think about these available decision toolboxes? What is their role in the development of edge intelligence? Who would like to answer this question? It's a very good question.
I can
Hello.
actually try to answer. I'm not sure what it means by decision toolboxes. It's if that means recommendation systems, as I assume. So usually in an AI model, you have like a result is a probabilities, list of probabilities. So you need to comprehend that list of probabilities somehow to action, and you can do that multiple ways. You can have a rule-based system, which is actually pretty easy to implement. It's just if and else. Or you can have something like a recommendation system that utilizes the pre-built probabilities, how likely something is going to happen, and how we should behave in certain system. So what comes to the actual recommendation systems, those are usually based on huge matrix operations, and there is some progress try to distribute those algorithms, and we can do distributed matrix operations, linear algebra in the distributed method. That's possible, but the current situation is that they are mainly focusing on the recommendation system field. Research is focusing on heavily on optimizing the performance, whatever is the computational load. So it's not considering that much the actual use case where you have like a huge amount of data and you need to perform something in real time or fast. So yes, we do have a toolboxes. What if they work or if they are suitable? That's the open question, and open resource question, and means that we need to consider more lightweight methodologies to actually run them on smaller devices, or a super big set of small devices where we need to do something distributedly. Then we need to consider whether we need central orchestration or central control over the system, like federated learning, or can we just do stuff automatically in truly distributed manner, where all of the nodes operate as individual coordinators of their own results. Okay, so there is a qualification question now. So this is some toolboxes, meaning any sort of decision logic system. So yes, you can have Bayes-based logistics system easily even in a smartphone. You can have easy logistic system easily in a smartphone, depending on how huge it is, of course, but easily. Its processing is nothing compared to what it means to process neural networks or some recommendation systems based on huge matrices. But is that enough? Maybe not, probably not. So if you consider even easiest models where we recommend products in Amazon web pages, or we recommend stuff for anyone based on some probabilities, or we provide multiple options based on a list of probabilities, introduce weights of the context variables, introduce the context in the decision making, then no, we don't have that computational capacity in a single device. And we need to consider a distributed model to do that truly, and there is still open work here.
And often research is done in isolation in one field and one topic, so that the same tools are being developed by different people who apply them to different problems, but it's still the tool development in some other field might be way advanced than it is in another one, and it's very challenging to find the right tools and to find the real state of the art, and that really calls for multidisciplinary research. So
and then usually actually those libraries are most effective in some statistical languages like R, and trying to run those languages and toolboxes and provide those for normal developers making applications for edge. It's not the optimal situation where someone who just want to have an app on the market needs to learn 10 new statistical languages to perform something. So yes, we need more toolboxes. We need APIs and access to its computing resources, but also capabilities that are possible to run over edge. So yes, this is a real question.
Exactly. The next question is about the autonomous driving scenario. So what type of AI algorithms models would be applicable to the autonomous driving scenarios in the future, considering the real-time requirements as well as the need for high accuracy even in corner cases? So autonomous driving scenarios.
I would just mention, because also Atakan probably will comment, but I would just mention that Ella has partially answered this just in the previous talk, because it somehow is highly connected, because all these models, this, let's say, federated or deep or whatever, it's also, these are tools which are necessary here. The question is very just in the sense that the key problem here in this autonomous driving and this driving is this very stringent requirements on the computation time. So even if there are some toolboxes, usually if you have such a mass scale of deployment and such stringent requirements on time, then simply we need to search for something else, right? Something which will work faster due to the requirements on latency and so on. So yeah, I will comment that.
Thank
Yeah,
you.
about the AI algorithms themselves, there was a very interesting discussion over which algorithms we can actually run. A keynote provided by Nick Lane, professor from Cambridge, this summer, and the conference that has terrible amount of letters in the word name, but I can post it if someone is interested. Anyway, the question is that currently the development of distributed AI algorithms that are capable of running on the edge is focusing on neural networks, the federated learning stuff and others, mainly because those are kind of hot topics. They have do a lot of capabilities where we can apply those things, but sometimes even easier models can be as effective. But of course, it depends on the situation a lot. It depends on the vertical, it depends on the context. And one thing which is not looked for, and that was then Professor Nick Lane's message, is the unsupervised learning. There is no effort on unsupervised learning currently on a distributed environment. And that will be open topic because for supervised learning, you need labels, you need information, pre-information, a lot of data processing. But if you can effectively solve unsupervised distributed learning that can learn, for example, autonomous driving scenarios, that would be massive development.
Thank you.
Also, one more comment that also is in line with some other questions about the connection with fog intelligence and how it was raised, the fog intelligence and connection to, between fog and edge. So simply, if you understood fog as the intelligence in this autonomous driving case, as intelligence deployed, for example, within the platoons or within the cars, and to perform something here and communicate with the edge. So simply also it's a very important case how to solve it. So also in our experiment, what we have considered is that we have this edge which performs some some decision, make some decision or suggestions, but also there is some local processing of data within the platoon, and then such a scenario is also quite I would say interesting in the research, and also it answers just a comment also to what Ella said. Yeah, so it's on this unsupervised or some mixtures or something like this. I fully agree.
Thank you. Then there was a comment.
Can I also add something? Sorry, sorry to interrupt. So not for this question, but the previous one that said, is there anything missing to deal with uncertainties or extreme events? So what I also want to highlight is the lack of real data. Ella already mentioned supervised data and unsupervised data. So to have some intelligent algorithms, we usually learn from data when you use machine learning, and there is a lack of real-world systems for edge computing. So the available data is a big problem, I think, and especially for failures which are very rare. So even if you have real-world systems, you will not collect a lot of failures all the time. So I think this is something missing at the moment.
Definitely. And
there is also continuation question about this. Has the self-supervised learning been used in distributed learning, and if this touches the reinforcement learning? So yes, there is effects to do that, but I haven't seen any working prototype especially in the edge environment. There are, if you look at the agent-based reinforcement learning on mobile edge computing, you would find some papers about the topic. But the event processing, all sort of labeling is with the real world context and labeling. This is the huge topic. As long as you have like a image database where you need to label the images, you usually actually use the human power, human crowd sensed power to do the labels, whether there is a cat or dog in the picture. You get the labels by crowdsourcing humans, and that's a big problem because the labeling is not really, it's a human work in the end of the day, most of the datasets. Then we do have those huge datasets, and then we can utilize those. But what will happen in you have a car and it's meeting the first case ever, a baby reindeer, and there is no data about the baby reindeers. We will have a dead baby reindeer after that. So that's not that straightforward. You cannot have the huge image database in your car.
Thank you. Then if we move on to, there was a comment about the aspects of the network coverage, so related especially to the autonomous driving and electric vehicles. So if automated electric vehicles rely on the network to manage charging, the network will offer 99 or 99.9% coverage. So failures and intermittent connectivity are very rare. Also, the electric vehicles even today are connected to the cloud at all times over the LTE networks, at least in those countries where there is decent LTE coverage. So this goes to Atakan. What is your comment on this network coverage issue and then the vehicles?
Yeah, this is a very good point, actually. Yes, the networks are getting more and more reliable, and with 6G it will be even better. But so in the scenario that I presented, the failure doesn't have to be a network failure. It can be, and but it can be also it can be a node failure, and usually these edge servers are, because they are deployed in remote locations without support systems like cloud computing, they are prone to failures. So this is another, for example, in one of the data sets that we used, 44% availability was observed, which is extremely low, but this was an extreme case. But yeah, this could happen. And also the vehicles, autonomous vehicles or electric vehicles, whatever, connected vehicles, let's call them, can be traveling in rural areas or going through tunnels and many other things that might affect connectivity. So it doesn't have to be a failure, but some reason why the data is not transmitted.
Thank you. Then one question is about the connection between the computing methods, algorithms, and then the hardware. So are there any aspects of synergetic development of computing methods, algorithms, and the hardware, like low loss electronics and power management for low power sensors? Any comments on the linking the algorithms and then the hardware? Not from this group.
I can only say that yes, of course there is. So of course we are following the low cost energy is one of the key aspects in edge intelligence in general and in the future 6G networks in general, because as we all know, the electricity and energy issues are going to be a big problem, are already problem. The amount of energy required by computing heavy systems is huge. So, and it will be even bigger in the future, considering the IoT systems that will cover whole cities or huge manufacturers and all those sensors. So there's certain solutions here under development are, for example, these non-electricity sensors, where the only activated in when reading, starting from older RFID tags to different sensors, where you can get the current context of the sensor by powering it, and usually they don't need any other power. So that's non-battery, non-electricity devices. And then different dedicated AI services for low-cost consumption are under development, or dedicated. I mean, like a dedicated AI service, AI chips, AI services are under development, and dedicated low-cost energy chips for running local computations are under development, and there are some prototypes. I would say just look at the Google, but that's not a good answer. So not really my specialized area. Very interesting works are available, but this is the clear direction, which is a little bit open still. So what we can do with electronics and engineering, and what we can achieve in the area, but definitely we need solutions, because the electricity is not going to be easy or cheap. And if we can, for example, power edge computing with, for example, this sort of electricity remaining from other systems, we can get achievements in sustainability too. Meaning we have like a wind power and it's providing too much. But currently, maybe we can use this like a remaining extra energy for building some AI models beforehand, before we need it. So energy is important topic.
Thank you, Ella. That really, the link to sustainability is really strong in the development of 6G, and energy efficiency in all forms is really critical there. We have time for one very quick question. It's about the open source activities. So which open source activities of edge computing are relevant for 6G Edge? Any open source activities, Ella, please?
There is a current activities in MEC, mobile edge computing activities, which are currently more related to the 5G, but whatever is in the 5G will be part of the 6G. So these are not too much, that they are overlapping development issues, of course. So if you want to contribute immediately, look for the 5G mobile edge computing.
Thank you, Ella. Thank you all panelists. Very interesting presentation, and thank you all attendees for listening and writing your questions. Really interesting discussions. So thank you all. I would like to share a few final remarks regarding the webinars. So what will happen next? So the registration is open for upcoming webinars. This was the 5th, and we still have 7 more webinars to come. And the next 2 ones, you can already register to them. So every week from now on, every Wednesday, we will have a webinar until mid-December, and you can start to register to the upcoming webinars. And we will send you the online feedback form regarding today's webinar, and we will also send the link to where you can find the video in the coming days. You can also find the previous webinar videos in YouTube. And the discussion continues in social media, and all recent activities that we will be doing in the 6G flagship, you will find more information in the 6gchannel.com. And there you will also find the link to the new 6G Waves magazine that was published on Monday this week. It really covers all the white papers and a lot of other activities that are taking place within the 6G flagship. So this concludes today's webinar on Edge Intelligence and 6G. Thank you very much for all of you for joining. Thank you. Goodbye.
Thank you.
Thank you. Goodbye.
Thank you.